from CERN virtual machine side. So what is CERN? And CERN, in some sense, you can think CERN as what is Linaro Connect. Well, what is Linaro? We are very distributed. If you look at where the people come in, it comes from many different countries. CERN employs a very small amount of people, more than 1,000 people, and we take care of infrastructure, the framework where we can host the physics experiments. But majority of people belong to different institutions, different universities, different scientific research institutions, and you can see the distribution based on nationality. So it's truly international collaboration. So where is it? It's in a very nice place. It's actually divided by the Switzerland and the French border. It's basically in Geneva. And you can see a 27-kilometer ring, that's an LHC. That's our biggest machine, biggest accelerator we have to this date. And on this LHC ring, we have 4 main big experiments. In total, there's 7 active experiments, but 4 big experiments you're constantly going to see on the news. And I'm again from CMS, so I'm on this side, and Joshua is from ATLAS experiments, he's on that side. So those are 2 biggest general proposed detectors, and we need 2 of them. So if you're looking for the new physics, so we cannot just build one machine, try to find something and then announce it. We need 2 group of people going to separate directions, building separate machines, writing separate software, and coming up with the exact same result. If you come up with the exact same result, that's when you can actually say it does exist. And also in the background, we have LHCb experiment, which is also the Geneva airport, so you kind of get the scale of what kind of scientific instruments you're building. So where is those instruments? So we hide them. They're deep underground, about 100 meters underground. This is done for the security reasons, also to do some coverage for the cosmic rays. And you can visit actually CERN. You actually can go down underground and visit those nice machines. So let's talk a bit more for machines. So this is a CMS detector. It takes about 40 countries and 172 institutions to design the machine. I think the whole process started in the 1980s. It wasn't done in the last few years. It was done over decades. It's about 28 meters long and about 15 meters in diameter. And it's about the same weight as the 2 Eiffel Towers, 100 meters underground. And we spent about $500,000 to build it, and that cost keeps going up as we still continue to upgrade the detector. So it's a huge scale, as you can see in this machine. And we also have ATLAS detector. It's even more interesting. So it's still similar number of countries, similar number of institutions, but it's bigger. So it's 46 meters long, it's 25 meters wide, and 25 meters high. So if you go to the cavern underground, it's very hard to actually see the whole machine. And it's about 1 Eiffel Tower underground. And also in this picture, you can see that this detector is not one single, basically, photo camera. It has a lot of small sub-detectors. So it's small detectors packed in one big machine. And this is the picture, if you go to underground and if you go for CMS, you're going to see this picture. So this is how the actual machine looks like. What I like to call is, that's our spaceship. But it's just underground. And it's a very beautiful machine. And if you do everything correctly, we did the hardware correctly, we did the accelerators correctly, we recorded the data correctly, we wrote the software correctly, and the CPUs work correctly, we get very nice pictures. And this is a picture from a CMS event display for the Higgs boson. In this picture, you can see what's happening if you get 2 proton collisions, and then you have the particles in all the directions. So let's start talking about how we do the computing. An interesting thing is also, if you consider that it takes about $500 million to build these kind of detectors, and you also consider how much the community invests for the computing and processing this kind of data, so 5 years of our computing is the same as building one of these scientific instruments. And we split our computing basically in 2 sides, what we call online and offline. So there are some systems which are very close to the detectors. So each detector is going to have some form of a farm, CPU-based farm, for processing the last level filtering of data before we're going to store them permanently on the tapes. So that's what the experiment owns. It's a single customer, basically. It has high bandwidth interconnectivity. And then we have a worldwide LHC computing grid. And that's very interesting. What we would like to call it is a virtual supercomputer. We don't own full hardware in it. It's basically 42 countries and 170, 180 computer centers around the world. So again, it has multiple customers. EMS is going to use it. ATLAS is going to use it. ATLAS is going to use it. Multiple experiments are going to exploit it. It has various hardware. So it's not the same silicon. So we're going to have more than 100 different CPUs from the last 10 years, probably. But if you look at the latest numbers, for example, I think we currently have about 650,000 x86 cores for processing this data. And CERN has about 200,000 cores of that. And we added another 100,000 cores just in a few months. In terms of storage, we are approaching about exabytes, and that's going to be divided in the tape and in the disk. And like, if you're interested in how much of data we are moving in this virtual supercomputer, it's about more than 800 petabytes in the last year. So, and this picture is probably going to change a lot in the future. So this is our grid, again. It's all around the world, 170 computer centers that's constantly changing. The number of cores are constantly changing. And the way the WLCG happened, it happened in about 2,000 years. And that's based on a commodity. We converge on the Linux operating system. We converge on x86. So one architecture, build software once, run it everywhere. So this is the model we continue to do. And that basically leaves us with only 2 vendors on the market for the silicon chip. So what happened in run 2? So the way we do things is in a run. So when we announced the Higgs boson, it was after the run 1. Then we had a long shutdown of 18 months, and now we're also collecting the data. That's what we call run 2. And at the end of 2018, we're going to shut down the detector, and we're going to have a 2 years long shutdown, again, to upgrade the machines to prepare for the next recording stage. So we now are in run 2. So what changed? So we tend to actually global rates across the WLCG doubled. We record about more than 10 petabytes of data a month. And in terms of what we need to transfer, overall, like in the peak months, we transfer from 80 petabytes to 100 petabytes a month during the peak times. And again, we transferred more than 800 petabytes of data across this grid. In 2016, we recorded about 75 petabytes data in total, which stores in the tapes for permanent storage. And we had some troubles. So we had expectations from a machine, and apparently the machine worked above expectations. So we have a lot more data than you did expect. So that, caused some issues for us. So how does it work? 42 countries about, 170 computer centers, all distributed around this big, nice globe. But we don't have one single batch emitter system. We use multiple of them. We have no single storage solutions, again, site depending. We have multiple silicon chips, more than 100 plus, I think, the last time I checked. So in 10 years, so everything from 10 years, we probably have it. Most of that is 4 to 5 years old. There's one common operating system, so everything is Red Hat Enterprise Linux based. Either it's Red Hat Enterprise Linux, or it's Scientific Linux, or it's CentOS. So this is the one common ground on what we build our software on. And we have a HAP spec 2006, which is basically CPU benchmark, CPU spec 2006 benchmark, what we use for accounting and the procurement needs. So the CMS is a virtual organization, ATLAS is a virtual organization, and WLCG is one bigger resource, and we need to somehow account of who uses and how much of resource is being used in this WLCG grid. So what is the future and what are our problems? So in about 10 to 11 years, we're going to have a thing called the high luminosity LHC, or we could also call it run 4. And so in 2016, LHC experiments record about 50 petabytes of data. And we moved about 800 petabytes of data again. For the high luminosity LHC, that's estimated for the first year is an exabyte problem. We plan to record 800 petabytes of raw data in 2027, and we plan to have derived data, just one copy, and we have multiple copies for safety, 900 petabytes of data. So our problem is becoming more bigger. And in terms of CPU, if you look at 2016, we need about 60 times more than what we had in 2016. The problem is our budget is flat. We do not expect to have more money in 2017, so each year we're going to spend the same amount of money for our computing needs. And if you look at that, if you do the math, you're probably going to be short by 10 times less. So the run 2, which we're doing right now, is the evolutionary process. We can handle that. The run 3, we also can handle that. The run 4, we probably also can handle, and the hardware and everything is moving to that direction. The problem is the price point on it. We have a flat budget. So in the run 4, in those 10 years, we have to go from evolution, and we have to think about revolution. How are we still going to handle that amount of data with a flat budget? So we started looking at ARM. For CMS, ARM started about 2013, and we did ARMv8 port. I think LHCb and ATLAS experiments might have done some of ARM stuff before that. And there was various reasons why we did that. We wanted to look at the performance, power consumptions, validation. Is it the same results we get on the physics side? Do we get the higher efficiencies? Can we pack more for those nice small cores and get high density systems but still kind of process more data in the racks? Geopolitics might play a role in this because, different regions might build different chips due to some limitations. And the business model of ARM is actually very interesting. It's flexible. So, we have better competition, so you have more players in the market. So you're going to go with one, or another one, or based on the regions. If even everything is not satisfying you, you can actually build your own silicon chip and continue to run the software. And if you start thinking of ARM and you saw the projections for higher luminosity LHC, you need to think, so how ARM can actually change that curve? Will it change it or not? So it's very interesting questions. So let's talk what we actually run in that WLCG. How does the experiment software look like? So on the left side, you have an ATLAS code base. And ATLAS have ported what they call a FINA simulation. It's just part of the full software stack, just doing a simulation. In the full size, ATLAS software is about 6.5 million lines of code. And that's custom for the detector, for that one experiment. CMS is another 6 million lines of code. That's, again, custom code written just for one experiment. So ATLAS did only the simulation. CMS has actually a full stack of our software running on 64-bit ARM. And in the CMS-SW side, you can actually see what we have. So a FINA and the CMS-SW actually consists of multiple packages. So it's about 2,400 packages for the FINA, and it's about 1,200, I think, packages in CMS-SW. So it's also divided into small packages. But we actually build a lot of stuff. We build everything from the tool chains, Python, Zlib, even glibc, and then a lot of HEP on HPC-based packages for our needs. So if you think of it, it's huge. It's 400 or even more now RPMs. And you can think it as a container software collection, or even almost getting close to a full Linux distribution. And all of that sits on Red Hat Enterprise Linux-based operating system. And again, if those 6 million lines of code dedicated for one experiment looks a lot, when you look at different projects like Root 6, also developed by CERN, that's another 1.7 million lines of code. Jan 4, which we're using for simulation, that's another more than 1 million lines of code. So the code bases are very huge, and those are very specific for high energy physics. And so we did the software. We know that it works. We know that that ATLAS simulation works. We know that CMS stack also works. And we did do a demonstration cluster. So we know that not only the software works, but we know that the infrastructure can also work. So what we did here, actually, we sent a job from x86 system from CERN to the Mustang board, which was sitting in the Princeton University. So that's 64-bit ARM solution. And we fetched the input files from Nebraska University, so we know that you can do remote IOs. We did the computation. We staged it on the local disk. Then we moved it back for the final stage out in the Brazil site, and from Brazil site, we actually moved it back to CERN, and then we looked back at the data. And then you do validation. So you see two plots. One is from ATLAS side, which is a simulation and reconstruction, and from CMS side, this is reconstruction results. So in CMS, we compared x86 with 64-bit ARM, and you can see that there's numerical differences. So even if you do the technical things, if you do the software right, and the infrastructure works, the software works, validation is important. We don't want to have the physics working differently on 64-bit ARM and different on x86. So even if you spend years optimizing the software and everything, it all comes down to these flaws, trying to figure out, is it significant? Is it good enough for the physics? And this is a very important point. So these are the histograms, but if you want to play a game, you can actually look at ATLAS detector. And these are supposed to be two identical events. One is on an Intel Xeon, another one is done on some 64-bit ARM platform. And you can start looking for the difference in these pictures. And you can see that, for example, on an Intel Xeon system, we have energy deposits in calorimeter, which is a part of a subdetector and detector, which we do not see on ARM system. Actually, if you look here, we also see that we lost one of the tracks on ARM. So there are differences, and we need to investigate if those differences are due to a result of a Monte Carlo process, or is something related to architecture, something that isn't stable yet in our software. So how many cores do we have? So this started 64-bit ARM in about 2013, I believe. That's in the first. We actually started from foundation model, moved to QEMU, and then we got the hardware. And we have been doing this for about 4 years, I believe. So the scale we are right now, or we're going to be in 2017, we're probably going to be approaching about a couple of thousands of 64-bit ARM cores at CERN. None of that is for production. Most of that you probably cannot even buy. It's only for reporting, benchmarking, optimization, and feedback to different silicon vendors, to platform vendors, to software vendors. And most of that, hopefully, going to be powered by CentOS 7. It's not going to be possible for every single hardware, sadly. So in that case, we're going to run in the containers. But this is the scope we hope to have in 2017, if everything goes correctly. And so where do we do this thing? How do we do this? So we have a Sunoco Lab. So we have a public and private partnership happening at CERN. If you're an industry company, you want to actually do a research, or you want to look for the problems which you can't solve at CERN, that's where we have a Sunoco Lab. So a lot of companies are part of Sunoco Lab, like Intel or Rackspace, trying to look in various problems we have. And it's divided into phases. And phases takes about 3 years. We are right now in about closing a phase 5. And you can see that we do have ARMv8 64-bit porting optimization benchmarking part of this phase. And we're also going to be discussing very soonish about what's going to be in the phase 6, which actually starts in 2018. So if you're a company and you're actually interested in solving some of the problems at CERN or full LHC experiments, even beyond that, write an email to Sunoco Lab CTO and say that you're interested. And before I give a presentation to Jakob, I'm going to talk about, just briefly mention a direction of community. So for the phase 6, there's going to be a Sunoco Lab white paper about computing challenges, which should land in September 2017. And there's also a broader paper coming from High Energy Physics Software Foundation called the Community White Paper. It has multiple working groups, so there's everything from machine learning to moving the data, workflow, resource management, everything. It's a lot. And it's much more broader. Again, it comes from a high energy physics community, so it goes beyond LHC experiments. And those two are going to have an overlap. So again, where is the link? So if you're interested in what our community is thinking for the next 5 to 10 years, go to this link, find the Google Docs. There's going to be descriptions of what's happening. And from here, I'm going to give the presentation to Jakob. Jakob.
Thank you. So David spoke about resources that are pledged to us. There are also resources that are more opportunistic and unmanaged, which we can use in addition. And we are using clouds, infrastructure as a service clouds, so EC2, Azure, GCE. We try to run on supercomputers on these machines where at some point you might find yourself in a situation where you cannot schedule one of these traditional big HPC jobs anymore, but in backfill mode, you can use the remaining free cores with HCP jobs, something we try to do. And also, we are involved in volunteer computing, where interested folks, they donate cycles from their private computers and help us do scientific computing. And this spans a wide variety of resources and environments, so obviously our applications and systems must be able to adapt. And I would like to speak about cloud and about volunteer computing. So what the clouds allow us to do is to run our resources at full capacity and to satisfy peak demands by commercial clouds. So peak demands you have typically just before conferences, when everybody needs to redo the plots. So there is a good chance that this theme of offloading peak demands we will only ever do for computing, and that we will always keep the responsibility for the data within the community, simply because we are very afraid that someone else might lose the data. Nevertheless, due to the rise of cloud and web companies, we have, there was great many distributed systems and distributed systems research, and we learned from that, and we can privately adopt all the things we learned about, using virtualized resources, scalable blob storage, NoSQL databases, and we have adopted products like OpenStack and Ceph and others to benefit from these advances. So one of the things we need to be able to do if we want to offload computing into the cloud, we need to be able to show that we can quickly ramp up computing. We can make use of a number of resources that are added to our system. And in this plot, you can actually see two things. You can see that the base load is provided by many relatively small, by a federation of relatively small sites and centers. But then you can see this, so on the x-axis you have consecutive days that, within very short time we can double the capacity. So this was at Supercomputing 2016. We got a grant from Google. And so during the day, we rented computing resources up with virtual machines on GCE. And, when people went to dinner and to sleep, we ramped it down again. No one was looking. So we learned how to do it. We learned, for instance, well, that actually, one more point, becomes ever more appealing as the prices of commercial clouds go down. So we are very interested in a manifold and broad market. Right, so we learned a few things. We learned that when we start the number of virtual machines very quickly, we need support structure, right? We need data caches, software caches, and we need an entity. So we have now a new free parameter. We do not only have a fixed set of resources, but we can decide if we want to create more resources or if we want to shut down virtual machines. So we need an entity that looks at the demands, that looks, for instance, at spot price market and makes that decision. So that is for commercial clouds. We have on the academic, on the private clouds, it seems converging towards OpenStack and KVM, most notably the CERN data center itself, which is a 90% OpenStacked, 200,000 cores managed by OpenStack, which is growing, as David was mentioning. 3 petabytes of volume storage provided by Ceph. So this is not for the physics data. This is really the virtual machine volume storage. And one interesting point is that our data center is actually 2. So it spans 2 physical data centers. What you see here is the CERN data center in Geneva. And you see the very high ceilings. So it's an old building. And in previous times, you had the Cray supercomputers in there. Now you have more the traditional cloud data center. And in this data center, we are limited by the amount of power we can pump in. So we have a remote data center, which is actually here in Budapest, Wigner Center, which is connected by 300 gigabit links to Geneva. Right, so logically, we see it as one big data center. So once you have a cloud interface, you need a virtual machine image to do something useful. And one of the things we realized when we started looking into clouds in 2008, 2009, was that so it's very challenging to build. You have seen these very big application stacks we have in high energy physics. If you package that into a virtual machine image, we end up with many gigabytes worth of images. And the next day they are outdated and you have to produce a new one, you have to distribute it to everybody. And what we did instead, we developed a file system that helps us distributing these software stacks. It's a CernVM file system, an open source file system that uses HTTP as a transport. So we store all the software, we install it into this globally available shared software area. And it's content addressed. We use it kind of as a Git for our software binaries. And the good thing is that from terabytes of software and hundreds of millions of files, for any given computing task, you need only a tiny fraction of that. So you need typically only a few hundred megabytes. And since it sits on the file system, so automatically you only transfer exactly the bits and pieces that you need. So that was a very efficient way to distribute the software. And that helped us solve the image distributions problem. And then we thought, nothing prevents us from not only storing scientific software on the file system, but also the operating system itself. So you see we have a few additional volumes with Enterprise Linux. It actually goes back to very historic versions of Enterprise Linux for historic versions of experiment software, for perhaps even decommissioned experiments. But we still would like to, or we still can reproduce these results, and we can compare them to contemporary experiments. So in the end, this leaves us with a VM image of a very small footprint, 20 megabytes, with a Linux kernel, with the file system client, and we ported all of this to ARM. So we ported the file system to ARMv7, ARMv8, and also the virtual machine. That was a fun project done by a bright student of ours. And so everything, the kernel was recompiled, and all the little utilities we use in the init RAM disk, busybox and partitioning utilities. And then we taught the virtual machine about GPT, partitioning format, and it shouldn't use the master boot record, but it should use ESP for booting. So in the end, we ended up with a UEFI compliant image, and it worked. So we tried it on Xgene1 servers and on brand new Cortex A57 based servers. And you have this, so you can define a virtual machine, we can start it. You have this characteristically long QEMU command line. You see it's accelerated by KVM. And we can log in, and we can actually run some real physics applications. And that is a very promising step. So we believe that that makes us conceptually ready for ARM-based clouds. And I would like to speak a little bit now about volunteer computing, moving from cloud to volunteer computing. Volunteer computing you might know from SETI at home, the search for extraterrestrial life, or Einstein at home, the search for gravitational waves. And we have also a few at-home projects, ATLAS at home, LHCb CMS, the machine itself for the 6-track project, and the CERN theory group with the Test for Theory project. So I encourage you to look up, and if you like, join these projects, help us do some scientific computing. And this is a means of doing outreach, but it is also doing some serious computing. So if you look, for instance, at the project at the bottom, Test for Theory, this project runs simulations, so we call it event generation. It simulates what happens when two protons collide. And by doing lots of these simulations, we can help the CERN theory group to improve their codes, to build more precise and better simulation codes. And for the CERN theory group, the volunteers is their biggest computing resource. Right? And if you look at ATLAS at home, If we combine all the volunteers, it's ATLAS' second biggest simulation site. So the traditional volunteer computing resource, a desktop computer, is a resource that is declining. Nevertheless, there's a whole bunch of new devices entering everybody's home. So for instance, in my home, I have a bunch of Raspberry Pis, and some of them I put in, I arranged in a Lego enclosure. This is actually building the CernVM file system for ARMv8 with a disk CC. And if I go to my friends' homes, they also have often Raspberry Pis or other IoT devices. So perhaps the future of volunteer computing might be if these devices are not running your TV, they might do some useful work. They could do some scientific computing. Or perhaps when your phone is charging, it could do some useful work. So here I've used EMS Krypton, which is a great piece of software that allows you to compile C++ code in JavaScript. And so it allows me to run one of our main simulation codes, the Pythia application, in a browser on my phone. So we want to see a whole more lot of physics in the future, and to do this, we need a whole lot of very powerful computing. And so sometimes we work on timescales of decades, so which is certainly longer than technology cycles. Nevertheless, so we have our version of Moore's law. If you look at the center of mass energy and the collision energy of particle accelerators over time, you will find an exponential growth. And so what we do is we prepare our software for a lot more data to come. We prepare our software for change. And we are also counting on change and technology innovation. If you want to get in touch with us, please write to us. If you are in Geneva, visit CERN. Thank you for your time.
So please, really fascinating topics this morning.